In this video, we will derive the equation for the torque transmitted by the circular shaft here. Okay, so we are discussing the circular shaft. In the previous video, we derived the relation between the angle of twist and the shear stress, right? The angle of twist is denoted by theta and shear stress is denoted by tau here. Okay, we derived the relation between these two here. That is just I'll write here. That is g theta by L equal to tau by r. This relation we derived in the previous video here, where g is modulus of rigidity of the shaft, theta is angle of twist, L is length of the shaft here, that is circular shaft, tau is the maximum shear stress. As I said, the maximum shear stress is developed at the outermost part. It starts from center to outermost. The center is 0 and maximum shear stress developed it is at the outermost surface here. Okay, that I already explained in the previous video here. And this r is the radius of the circular shaft. Okay, so now in this video we'll derive the equation for the torque. Torque is normally denoted by T here, and it is in terms of like shear stress. We will go one by one here. Okay, so for that we'll start with the circular shaft. Okay, I considered here, see, this is whatever the circular shaft of solid with radius r, okay. So consider circular shaft shown in figure. Okay, let r equal to the radius of the shaft, and tau. Here tau, it will comes, what you mean by tau? Tau is the shear stress. Shear stress developed at the at r here, that is outermost surface. Okay, so here is maximum shear stress. Okay, so shear stress, that is maximum shear stress at r, that is at radius r here. Okay, so to analyze or to get the torque here, first we will consider a small elemental ring here, and we will derive the torque on that elemental ring, and then we will integrate. We will get the torque, total torque on the shaft here. Okay, so I am considering here the elemental ring which is at a distance of r. Its distance is, the ring distance is r from the center. Okay, and its thickness is dr, here. Okay, consider small elemental ring shown in figure. Let what is small r here? Let r equal to the radius of the ring. Okay, elemental ring. And what is dr? Dr is thickness of the elemental ring. So now as I said, this tau is the maximum shear stress at r, capital R. Okay, so now I am consider the Q. This will be equal to shear stress at a distance of small r. It is at the elemental ring. Okay, the shear stress developed at here, whatever the shear stress is generated, that I am denoted by Q here. Q is shear stress induced at r, that is on the ring here. Okay, now these are all the data. Now we will consider we are considering this small elemental ring. So in the previous, as I said in the previous video, we derived the relation between the angle of twist and the shear stress. That we need to continue from that here. We know that tau by r. Tau is maximum shear stress and r is radius. You just remember this is the maximum shear stress that to develop at the outermost surface. Okay, so maximum shear stress divided by r equal to g theta by l. Okay, g theta by l. This we derived in the previous equation. So from this equation, g is modulus of rigidity. It is constant for the given material. Theta is angle of twist, that is also constant. L is length of the shaft, solid shaft, that is also constant. So all these three, the datas are constant here. These three datas are constant, so tau by r is constant. Since for given shaft, g, theta and L are constants. Therefore, tau by r equal to constant. Okay. So this tau by r, it is constant. Now for radius small r and for the given shear stress acting at r at the elemental ring, that is also the tau by r is constant. Therefore, for radius r, small r, for radius small r on the ring and shear stress q on r this tau by r equal to q. What is the q? Is shear stress at elemental ring divided by r is the radius of the elemental ring equal to constant. Okay, this is one of the relation. Wherever the maximum shear stress to the outermost radius is, the ratio of that is always equal to for any given radius and the shear stress, and that at that point it will be if the ratios are constants here. Okay, that is the one relation. So from this, what we will get here, therefore the shear stress, this is the shear stress at elemental ring. Therefore q equal to what I am getting here, maximum shear stress into radius on the elemental ring divided by r here. Okay. So this is the shear stress and the elemental ring in terms of maximum shear stress. Now we will go to the turning force developed onto the elemental ring. Turning force means whatever the rotating force developed on the ring. Turning force on elemental ring equal to, we have the formula turning force for that is shear stress into area of elemental ring. See, just I tell, this will be shear stress on the ring is Newton per mm square. This is Newton per mm square, and area on the elemental ring is mm square. This cancels and it will get in terms of Newton. So that is the turning force on the elemental ring here. Okay, so that's why I wrote in terms of shear stress and the area here. How will okay, now this will be equal to q into what is the area of the elemental ring? I'll just denote it by dA. This is area, where the dA equal to area of ring. How will you calculate area of ring in terms of small r? That will be equal to 2 pi r into dr, right? This is the area of the ring here. Okay, so this I'll substitute here. That will be equal to q into 2 pi r into dr. This is the area, and this is the shear stress on the elemental ring. So what is the Q shear stress on the ring? Here, substitute this value here, that is, this will be equal to tau into R divided by R into 2 pi R into dr. Okay, dr. So this is the turning force generated on the ring. Now once if you calculate the turning force, we can calculate the turning moment or torque. Both are equal. Turning moment or torque is the turning force into the distance from the center to the ring. Distance from the ring, that is force into distance. This is the force. Distance is, that is the from center to the ring, that is R. So now we will write that one here. Okay. So next one is turning moment, because I want a turning moment or torque on the elemental ring. Then we will go for the whole shaft. Therefore, turning moment or torque on elemental ring. What I can write here? Turning moment, turning force on the ring into distance, that is turning force on ring into distance from the center, from the axis center, from the axis of center, from the center to the ring, right? So how much is the turning force? Here we calculated here. This I will write here. Turning force is tau into R divided by R, 2 pi R into dr, right? Now, what is the distance from the center to the ring? Center to the ring is R. This is R. Okay. Now I will erase this one and we will continue. So now simplify this one, that is turning moment. Just I'll write torque dt, because this is small torque acting on the elemental ring, dt. This will be equal to tau by R, 2 pi R square R cube. This is R cube into dr, right? R cube into dr. So this is the total the torque acting on the element. Now if I want the total torque on the shaft, I need to integrate, right? I need to integrate from 0 to capital R. To get total torque on shaft, I need to integrate, that is the 0 to R, 0 in the center and R, it is dt here, This will be equal to, I will write the T, that is T, that will be equal to integration of 0 to R, tau by R, 2 pi R cube into dr here. Okay. Integrating the terms, we will get the answer here. Just I will integrate, remove the separate parts, that is tau by R, 2 pi into 2 pi. I will take the outside, integration of 0 to R, R cube into dr. Okay. So this will be equal to tau by R into 2 pi. Yes, after integrating this, I will get R raised to 4 divided by 4, 0 to R here, 0 to R. Now substitute the upper limit and lower limit. That is T, this is total torque on the shaft, T equal to tau by R into 2 pi divided by the R raised to 4 divided by 4. Okay. So this will be equal to tau by r into pi into r raised to 4 divided by 2, right? So here one term it will comes. I'll substitute this value as jp, j suffix p. Thus I'll tell what is that. Tau by r equal to jp. What is jp? Jp is polar moment of inertia. Polar moment of inertia, where jp equal to polar moment of inertia. What is its value? Its value is pi r raised to 4 divided by 2. This is the value. In terms of d, this is the radius r. In terms of d equal to 2 times r, right? Or r equal to d by 2. R equal to d by 2. If substitute in terms of d, just what happens here? Pi into d by 2. This is d by 2 raised to 4 divided by 2, right? So how much I'm getting here? That will be equal to pi d raised to 4 divided by 16 divided by 2, right? So this will be equal to pi d raised to 4 divided by 32. This is called polar moment of inertia. Polar moment of inertia is pi d raised to 4 divided by 32. It is the moment of inertia about the centroidal axis. Okay. The moment that will be equal to moment of inertia of transverse section about the centroidal axis, about the centroidal axis. Okay. So whenever we will get the j, it is pi d raised to 4 divided by 32. We need to substitute. Now this is p, torque. I substituted here. Okay. So here t by, if the after simplification, t by r, that is t by jp equal to tau by r, right? Tau by r. This is one relation I am getting here. So in the previous video we derived the one relation between the angle of twist and the shear stress. Just I'll write that one. The g theta by L equal to tau by r, because we started the same from this equation to derive this, right? So here tau by r, here tau by r, same, right? This is also one equation in previous we derived. So from these two equations we can write t by jp equal to tau by r equal to g theta by L. This is the important derivations related to the angle of twist, modulus of rigidity, length, maximum shear stress, radius. This is the torque, turning moment, and the polar moment of inertia. This is one relation here. Okay. So from here we will get here from this. Okay. So now I'll continue the total torque. Because this is the intermediate, I derived these three very important relations here. Okay. So now I'll continue. What is the total torque developed here? From here. Okay. From this. Okay. So this is T, right? Now from this one I'll go here. Okay. So T equal to tau, substitute R equal to, what is the radius? D by 2. That is, I'll substitute D by 2 here, and next pi D by 2 raised to 4 divided by 2. Okay, where R equal to D by 2. So now how much I'm getting here? That is, this will be equal to tau by 1 into 2 divided by d into pi. This is d raised to 4 divided by 16 divided by 2 here, right? So this will be equal to, sorry, here pi is missing here, this is pi, here also pi we will getting here, okay? So pi into tau into 2 divided by d, this is pi d raised to 4 divided by 16 into 1 by 2 into 1 by 2. So these two will cancels here, and d and d here will cancels, and finally we will get the total torque developed maximum torque. Therefore total torque developed, how much I am getting here, that is pi into tau, this d. So here only one pi equal comes, right? Only one pi equal comes here also. Sorry, I already substituted here, that is pi tau into d cube divided by 16 okay. So this I can write simplification, pi by 16 tau into d cube. This is the maximum, the torque. It means the maximum torque or maximum turning moment at the outermost, the surface of the shaft developed. Pi by 16 times what is tau, maximum shear stress developed at the outermost surface, into d. D is the diameter of the shaft here, okay. This is the important equation here. So from this total derivation we will get the important equations are, this is one maximum torque developed by the circular shaft, it is pi by 16 tau into d cube. So one more, g theta by L equal to tau by R, this is one relation. So one more relation, T by Jp, right? T by Jp equal to tau by R, one relation. We are getting, just we derived just now, this we are derived in the last class, and from these two we are getting g theta by L equal to tau by R equal to T by Jp. These are all important formulas we need to remember here while solving the problem, okay. This is how we need to derive the relations here.